My name is Luke Outtram, and today I will be explaining what the halting problem is and its importance in computer science. To begin with, one has to understand the term decision problem. A decision problem is a problem that can be phrased as a yes or no question of the input values. For example, given two numbers x and y, is the sum of x and y an even number? The answer is either yes or no, thus making it a decision problem. This leads us to the concept of decidability. The example I just used is classified as a decidable problem because it has a solution. It's not important if the answer is yes or no. What is important is that the answer can be proved. In computer science terms, if we can create an algorithm that comes up with a solution to a decision problem in finite time, then that problem is decidable. But what if that algorithm cannot find a solution in finite time? As far as we can tell, it could just keep running and never provide us with an answer. In that case, the problem is known as undecidable. Here is an example of a well-known undecidable problem. It is known as the game of life. This is a dead cell and this is an alive cell. The game follows this simple set of rules that determine whether or not cells die or reproduce. Here's an example of what the game looks like when run. It seems fairly straightforward, right? Well, in general, it is. Most seeds, starting patterns, will expand and break down into recognizable patterns in finite time. However, some seeds don't stop expanding. They don't stabilize or terminate, they just keep growing. Of course, given enough time, such a seed may eventually stabilize, but it could continue forever. This is what makes the game of life undecidable, because there is no algorithm that can predict, based on a given state of the game, whether or not that state will terminate or continue forever. So unless somebody finds a solution to this problem, the game of life will remain undecidable. But what the halting problem tells us is that we could search through an infinite number of solutions to the game of life and never find one. In order to understand how the halting problem demonstrates this, we have to go back to the 1920s, when German mathematician David Hilbert decided to try to unify mathematics. This attempt was known as Hilbert's program and worked under a few key assumptions. 1. There are no undecidable problems. 2. We have complete knowledge of the axioms that support mathematics. What Hilbert was trying to do can be summed up in one question. Is it possible to determine if any decision problem we are given is either true or false? This is when Alan Turing came along and used the halting problem to show that the answer is no. The heart of the halting problem is this. Can we determine if a program and its input will halt or loop forever? Turing proved this is impossible by first assuming it was possible. Firstly, he imagined that there was a machine, we will call it a magic 8-ball, that given a program and its input could predict whether or not that program would halt. So if we gave that 8-ball the game of life, with a starting seed that terminates, the 8-ball would output halt. Now imagine if we add an inverser to the 8-ball, one that inverses the 8-ball's output. If the 8-ball outputs halt, then the final output will be not halt. For the sake of simplicity, imagine the 8-ball and inverser are one machine, called the Barry machine. But what if we fed the Barry machine into itself as the program and the input? If the 8-ball predicts that the Barry machine will halt, then the Barry machine will output not halt. And if the 8-ball predicts that the Barry machine will not halt, then the Barry machine will output halt. Either way, it's a contradiction. It's a paradox, because whatever the Barry machine tells us it is going to do, it does something else. Therefore, our initial assumption that there is a machine that can determine if a program will halt or not exists was wrong. So what are the implications of this? There's no way of knowing if a program will halt or not. Therefore, undecidable problems exist, because some programs could be searching an infinitely large search space for a solution to a problem and never find them. Thus, Hilbert's program could never work because his initial assumption that there are no undecidable problems was wrong. Although it's disappointing that some problems can never be solved, undecidable problems can also serve as a source of motivation to expand our knowledge and problem-solving abilities.